Okay, so this is an 8.5 by 11 sheet of paper, and what we're going to do is we are going to cut squares out of the corners. Okay, so we're going to cut squares out of the corners, and then the size of those squares is allowed to be different, right? So we can cut real small squares or larger squares. Okay, so we have lots of options of how to cut out these corners according to the side length of the square corner. Okay, so this looks about right here. So we're going to cut those corners off. Okay, we're going to cut them out, and what happens is what's left is kind of flaps. When we take those corners off, we're left with flaps, and then we can fold those flaps everyone say ooh, and then we get a box without a top, right? So you fold those flaps up, you get a box without a top. Okay, so there's lots of things we can talk about here in terms of changing quantities, right? So there's all kinds of quantities involved here we can talk about as changing quantities. Okay, so again, one more time. So we start with an 8.5 by 11 sheet. We cut out squares of various size. So, and we cut those squares out, and then we fold up the flaps to create the box without the top. Okay, so does it make sense in your mind? Got the scenario down? Okay, cool. So so here's the same thing, and over here this shows the flat piece of paper on the table, like looking down on it, and then over here shows the resulting box as we pick different size cutouts. So do you see how this is exactly what we just talked about? Okay, so let's just say that the cutout length is right here, and let's talk about, so let's kind of brainstorm on what are some changing quantities that are involved in this situation. What are some changing quantities involved in this situation? What do you think?
The volume of the box.
Okay, does the... Okay, go ahead.
In cubic centimeters.
Okay.
As the would that be the perimeter of the cutout in centimeters?
Oh, let's just do one at a time here. So he said the volume of the resulting box. What do you think about that? The volume of the resulting box. Changing quantity? Does it change? Does the volume change? Absolutely, right? Absolutely. Okay? So we got the volume of the resulting box. What else? What else is another changing quantity we could talk about here? Yes, sir?
The area.
The what?
The area. Surface area.
Surface area of the whole box? Yeah, okay. Sure, surface area of the whole box. What else? So surface area of the box. Does someone put their hand up?
Height and width.
Okay, the height of the box, called h. Does the height of the box change? All right, so and I can show that right there. Okay. So for this particular situation, there's the height, but it's a changing quantity, h, right? What else changes? Yeah, someone can say the width. So the width of the box? The width changes. Here's the width at for a particular box, here's the width of the box. What else changes? Length? Okay, so we got the width, length, and the height of the box. Certainly, all those dimensions change, and as those change, the volume changes. What is the formula for the volume? How do we calculate the volume?
Be length times width times height.
Yeah, so it's a rectangular box, so that's easy formulation. Remember, L times W times H. Good. So we kind of have overlooked maybe the most obvious changing quantity. What other changing quantities are there?
Box material.
Is box material a quantity? No, the material is not an object. The material is an attribute. It's an attribute, but it's not what? Why isn't it a quantity? The material. It's not measurable, right? Our quantities are measurable attributes. Measurable attributes. Okay. So there's an attribute, the material of this, the paper, whatever, cardboard, but it's not a measurable attribute. Remember, quantities are measurable attributes of objects.
But if you were to weigh it, you could say the changing quantity of the weight of the box material.
Okay, so the box, the weight of the box does it change? Yeah, because we keep removing more and more. We keep removing we remove a different amount of paper each time from the corners. There's still one kind of key changing. It's like the starting point for all the changing quantities.
So that would be the amount of material being fed from the box.
And how the amount of material? So what quantity do you want? What's that? Those what?
The area removed.
The area removed. Okay, so it's a little indirect though. Like so, when we want to determine the length and width and height, what is the quantity that's going to enable us to find the length and width and height? Yeah, right. So the length of the cutout, right? So those, yeah, the area. You could say the area that's been cut out. That's true. That's just a little more indirect. So we're going to call that x. So the side x is the side length of a square cutout. And we'll say, so in inches. Okay, these are all good changing quantities. Okay, so x. All right, what about constant quantities? So here's our list of changing quantities. We talked about volume, surface area, height, x, width. What about, tell me your name right here. Yeah, what about constant quantities? Anything that remains constant in the situation as these other things change. Robert?
The beginning area of the paper.
Okay, the starting,
8.5 by 11.
Okay, so the area of the paper. What else about the paper is constant? Yeah, so the original length and width. And do you see that those stay the same as we change the square cutout? We still have. Do you still see how that original length and width is being maintained? Can you see that dimension? So, what?
Change in height.
What do you mean the change in height?
That you're saying the length and width isn't changing, but the height is.
Yeah, the height of the box. Yep, we got that right here. The height of the box changes, but the length of the original piece of paper and the width of the original piece of paper, call those capital L and capital W, those don't change, right? See how those are maintained as we change the cutout. I kind of missed over here. There we go. Okay. Okay. So what we really like, we want to focus. One of the things we want to focus on is this volume equation. And since the very first thing we do is we cut out these squares, right? And so that's like kind of like the starting point changing quantity. So it'd be nice to be able to write this volume in terms of this cutout. So we cut out the squares, some length, and then have a formula based on that length that gives us the volume, right? Based on that cutout length. So in order to do that, we need to get L in terms of x, and we need to get W in terms of x, and we need to get H in terms of x. Okay, so L. Here's our length of the resulting box. Where does this length, the length of the resulting box, show up in this view of the paper? So where does this length right here show up in this view of the paper? How can you describe where this length is? Is it this length? No. So
Is that where the folding image is the link
what's that?
where it folds?
The folds.
Yeah.
So from here
Yeah. On both sides.
down to where?
Right there.
He's saying this. What about this? Is this our L, our length of the resulting box right there, from there to there? Yeah, that's it. Okay, so that's it right there. So I'll do that in blue. So from here to here is our little L, right? So that's the same as that right there. Okay, so what I want you to do is find that little L in terms of X. So what is, we want L in terms of X. So L written as something with X's. Okay, so take a moment to figure that out, and maybe you might just confer with the person next to you. Take a moment and confer with the next person next to you. What is that L in terms of X?
The whole page without any cutout is 8.5 by 11 inches, right?
Right, so this capital L, we know it's a constant quantity. What that constant quantity is? 11. Thank you. So that L right there, this L right here, is 11 inches. And the capital W, original piece of paper, 8.5. Okay, so go. So figure out what this length is in terms of X, an expression using the side length of the cutout. And then just check with the person next to you, see if you guys get the same thing. And while you're at it, let's do little w too. We're going to need an and h. Let's do all three. All three. So little w, little l in terms of x, w in terms of x, h in terms of x. All three. That way we can get volume in terms of x, right?
There's the little L's.
So it's
Marcel?
Are you giving us X?
Yeah, like a little cutout.
No, it could x is a changing quantity. It could be a small square or it could be a large square.
So you just want to formula.
In terms of x. In terms of x. L in terms of x. That's right.
I did like any like big L.
so we're trying to have
So your H.
Yeah. No, like a little L. And then split it. Like from a dotted line.
is the vertical cutout the
So
same
like that would be.
length as X?
The vertical cutout.
Yeah, like you know how you're cutting it out. Right.
If they're squares.
Okay.
Yes, yes. The corners are squares. So every dimension of these is x. Every dimension, when you cut out these, they're all x. Okay, is it Cooper?
No, I'm trying to
How
find.
did you get L in terms of x?
In blue right here, the little L, yeah.
What do you think? So how can we write this L in terms of this cutout little x? What would it be? Not sure. Michael, did you get it? Not sure. Okay. Adrian? What do you think? And how did you get that? Why? So he's starting with our fixed quantity of 11, but it's shorter than that, right? How much shorter is it than 11? How much on this side? How much shorter is it on this side? X, right? So whatever we choose for X, it's gonna be that much shorter over here, but then also this much X shorter over here. So therefore, He said 11 minus 2x. Make sense? What about the resulting width of the box? Start at 8.5. Who's saying that? Go ahead. Yeah, so we're going to take away x on this side for the square on the left, and take away x on this side, the square on the right. Which means little w is 8.5 minus 2x. What about the height of the box?
It's just an X.
Okay, so you should be able to see when you fold this thing up, there it is. So if I were to fold this flap up to the left there, there's the height right there. That's the height. Okay, so we can write the volume. Now all in terms of the one variable x, because we said volume is length times width times height. And so we've got length times width times height. And we got a formula for if we cut out, it's like a streamlined formula, right? We could choose any cutout square and take that square side length, we plug it into here, and it gives us the volume of the resulting box because it calculates the length, the width, and the height, and we multiply them together. Okay, so we want to focus on, let's take a few minutes to focus on this formula here and this one. So this is what? The length in terms of the side length, square cutout, and the volume in terms of the square cutout, and this will be a little bit of review, and that'll be good. And then that'll kind of push us on to the next topic. So we're going to focus on, again, this length as it changes with respect to the changing x and the volume of the box, changing with respect to x. Focus on those two. Okay, so we'll start over here on the left side of the screen. With the relationship of, here I've got this cutout side length on our x-axis, our horizontal axis, and I've got the length of the resulting box, which we called little l, not big L like that. So we'll change it. Okay, so we call that little l. And so what happens? So what is this showing right here? What is this? What are we showing? That if the cutout side length is 0, then what is the length of the resulting box? 11. We did so. Is this a valid kind of mathematical situation?
Yes.
It doesn't. So it may feel uncomfortable because it doesn't actually give us a box, right? What are we left with here in this situation here? Just the flat piece of paper, right? We just have the flat piece of paper, okay? But it's a completely valid mathematical situation. You can cut out squares of side 0. You can do it. Physically, you can do it, okay? And then you get this resulting quantity L to be 11. Okay, so what we're going to do is we're going to look at changes in X and the resulting changes in L. We've been talking about how, calculus is all about how quantities change together, and we've been working with the mathematics of that. Okay, so we're gonna look at changes in X. Let's have a little bit of room here, and the resulting changes in L. Okay, so we'll start with X going from 0 to 0.5. If X goes from 0 to 0.5, what is the change in X? Hopefully we all know that, right? 0.5. Starts at 0, goes to 0.5, then our change in X is 0.5. Okay, so I'm going to do it. Ready? Here we go. And what's going to happen to the length when I do that? Going to stay the same, increase, or decrease? Decrease. Okay, so I'm going to Hopefully a little bit more. There we go. Okay, so what happened? So I just increased the side length. We started at 11. I increased the side length by half an inch. And what happened to the length of the resulting box when I did that?
Changed by -1.
He said it changed by -1. It was at 11 before, and so when I cut out 2 squares of 0.5, the resulting length is 10, right? And you're seeing it right there. So we get a new point there. So the resulting delta x was, sorry, delta L, -1. Should make sense. If I cut out half an inch on each side, then the resulting length of the box, you can see it in the pink bar there. The change is going to be 1 less if you cut off a half inch on either side. I'm going to do it again. So I'm going to go from x goes from 0.5 to 1. April, what was the change in x?
0.5.
0.5 again. Okay, I'm going to show it. Here we go. Ready? Here it goes. Here we go. So what happened? We changed x by 0.5. How much did the resulting length of the box change? -1. I took off another half inch. I increased the side square cutout by another half inch, so that took off half an inch on each side, which made the length shorter by a total of 1. Okay, so now from there, I'm going to take x from 1 to 2. Okay, so we got, currently the x is at 1. I'm going to increase that cutout square side length from 1 to 2. What was delta x? What was delta x? This time I increased each cutout by a whole 1. So delta x was a whole 1. And how much did the length of the resulting box change? It went down 2 because I took off 1 on each side. Okay, so that was delta x of what? 1. Okay, finally, I'll do one more time. I'm going to go x this time from 2 to 3.5. Okay, so predict what's going to happen. So now I'm going to increase the square cutout side length, starting at, it's now at 2. I'm going to increase it to 3.5. What's going to happen to the change in length? Go, talk to the person next to you.
Oh yeah. We're increasing. I didn't get that.
Okay, so we've digressed already. Okay. So, what's your name right here? Dustin. Tell me about, so I've changed x by 2 to 3.5. What was the change in x? Okay, he wants the change in x. Sorry, how much was the change in x? 1.5. And resulting change in length? 3. What do you think?
-3. They forgot the negative.
You want -3? What do we think? Let's see. Okay, so I'm going to go from 2, here we go, 2 to 3.5. Close enough. And we went down, so that time the delta x was 1.5, and the resulting length of the box goes down 3. Okay, can you comment on what can you comment here? So I'm showing you changes in x, corresponding changes in the length of the resulting box. Can you comment on this and make any observations?
Constant rate of change,
Why?
because for any change in x is the equal change in L. Well, it's not an equal change, but L changes by the same amount each time.
Okay, so you're talking about, he's saying that you can always calculate the change in L by what? So can you be more specific? You can always change.
By the change in x.
Okay, so yeah, by the change in x, and specifically, how do we,
Times -2.
Marcel wants times -2. What do you think? Constant rate of change means changes in one quantity are the same constant multiple of changes in the other. This is a huge point of our first couple weeks, right? And what is that constant multiple? -2. -2 is the constant rate of change. For every change in x, our length will go down, will decrease twice as much as the change in x. So our constant rate of change is -2. Okay? What was another aspect of constant rate of change that we can talk about here? So that was one of the three, right? Changes in L are a constant multiple of changes in x. What else? How else could we argue about constant rate of change here?
They like maintain a constant ratio.
Okay, what ratio are you talking about? The ratio of
The ratio of x to L,
x to L.
or the change of x to L. The change of x to the change of L.
How about the change of L to the change of x?
Or, yeah.
Yeah, so that constant rate of change, we change in the y quantity over the change in the x. And what is that constant ratio? That's our -2. Yeah, so watch out for, so what about L over x? Does that maintain a constant ratio? Definitely not, because x is going up and L is going down. There's no way that L over x can maintain a constant ratio. Okay? If one goes up while the other one goes down, that ratio is going to change, right? But changes in L. So every time we see that the change in L, -1 over 0.5, -1 over 0.5, -2 over 1, -3 over 1.5, maintains this -2. What was the last aspect of constant rate of change? Tell me your name right here. Nope, in front of him. Yeah,
The other one was
remember?
just consistent change. I don't remember.
Yeah. Yeah, how do we get consistent changes? When do we get consistent changes?
When you change it.
When you, how? Yeah, go ahead.
The change in delta x is all the same.
Yeah, so if you keep equal changes in x, you're going to get a consistent change in y also, right? So equal, so here, there's one example of that. Every time I did delta x by 0.5, I got the corresponding change of L of -1. So there's just one example of that. But we could do more, right? So we could do a bunch of changes of 1. We'll always get a change of L of -2. We do a bunch of changes of 1.5. We'll always get a change of -3. Okay, and then we know that taking all the ordered pairs of L and X together according to this relationship, what creates a line, right? Creates a line. So, how many points on that line? How many points on that line? Many, many, many points. Not just one, right? I'm just highlighting the last point. These are all points, right? These are all points of a cutout length and a corresponding length of the box. Okay? So now let's move over here to volume. What do we have for our volume formula? We got?
B equals 7 minus 2x times
That's the length, right?
8.5 minus 2x.
That's the width. Length times width times height, right? Length times width times height. So now I'm, again, from the cutout side length on our horizontal axis, That's the blue arrow. And then I'm putting the volume on the horizontal axis. So when the cutout sign length is 0, what should the volume be? So if I put this blue arrow to 0, what should the volume of the resulting box be? Jacoby, question?
If it's 2x,
Thanks.
then
All right, you still want to answer my question?
Should be 0.
Yeah. Yeah, so when I put that, in what situation is that with the paper in the box?
paper's flat.
Paper's flat, right? I haven't cut anything out. Is it an okay situation? Is it uncomfortable? You don't get a box, but it's physically possible to cut out squares of 0. And you just have a piece of paper with a volume of 0, right? So here's that. There it is, right? So I changed the cutout length to 0. We got our flat piece of paper, volume 0. So I'm going to start with, now I'm going to do changes of x and changes of v. Same thing. I'm going to do the first change in x from 0 to 0.5, which is a change in x of 0.5, and I want the resulting change in v. So here it is, ready? Whoa, there I did it. Okay, I just changed the cutout from 0 to 0.5, and I got this resulting volume. So I want you to find the change in volume that just occurred. Go, find the change in volume that just occurred. Okay, so in order to do that, you take the change in x, you put the change in x in here, right? And it gives you the change in volume. Is that right? You're shaking your head. What's your name again? Alex, why not?
You can't input the change of of x. You have to input the same value for v, and then put in the next value and take the difference.
Okay, yeah, so this, if you put a number into here, what does it think it is? Does it think it's a change in the cutout? No, what number is it interpreting it as? A cutout side length. So in order to get the change in v, and you get the last practice on this in your web work, right? To get the change in v, you got to plug in what? Plug in 0 and get the volume at 0, and then plug the volume and get 0.5, and then do what? Subtract. So the volume at, say, we'll choose volume at 0, volume at 0.5. What's the volume at 0? 0. What's the volume at 0.5? 37.5. Okay, so in this case, that difference happens to be what you get when you plug in 0.5, but that's only occasionally does that happen. So we need the change in volume is the final volume minus the initial volume, just like you practiced a couple weeks ago. Final volume minus initial. Okay, so now I'm going to put in from here, we're going to go from 0.5 to 1. Tell me the change in x. Omar, what's the change in x? I gave you a nice easy one. Just hit it out of the park. Change in x from 0.5 to 1. Ethan? 0.5. And so then the corresponding change in volume will be, since equal changes in x will give equal changes in v, so it'll be 37.5, right? Okay, verify it. So verify that we're going to get a change in volume of 37.5. Go. So find the change in volume, 37.5, right? Anybody got V of 1? Tell me V of 1.
58.5.
58.5? Did I hear that right? What's the change in volume as this cutout side length changes from 0.5 to 1? How much did it change? 21? Uh-oh, what did we do wrong? So let's see it. Here we go. Ready? So from 0.5 whoa, to 1. Even so, it looks like the graph is showing the same thing that the numbers are showing. So we did 0.5 again for delta x, and the graph is showing us lesser change in v. What's going on here? I thought that equal changes in the first quantity are supposed to give consistent changes in the other.
If it's a constant rate of change.
He said if it's a constant rate of change. So conclusion? Tell me.
It's not a constant rate of change in space.
Yeah, so the volume does not change at a constant rate with respect to side length. The length of the box does, but the volume does not. And so we see this evidence right here. We got two equal changes in x and a non-consistent change in resulting volume. Okay, let's do it one more time. How about for 2 to 2.5? So one more change of 0.5. So go from x, go from 2 to 2.5 and find the change in volume. Good practice, okay? What's the change in x? From 2 to 2.5. 0.5. Okay, find that corresponding change in volume. Go. If x changes from 2 to 2.5. As soon as someone gets it, shout it out. Did you get it? Negative 10.5? Oh, what, this is getting really bad now, right? Now it's going down. So not only, so before at least they both went up, the different amount, now it's going down. Now the volume is going down. When you had a cutout length of 2, you increase it to a cutout length of 2.5, the volume decreases.
Because the box is rectangular.
Show you. So save that question. I'll show you the visual again. You can kind of see it. So here's 2. Mark that point. And then go to 2.5. So over here we get, starting at 2, we got this same change in x of 0.5. And now we're going down. Change in v, negative 10.5. So not only is it non-constant rate of change, but sometimes when you increase x, the volume goes up. Sometimes when you increase x, the volume goes down. Okay, so if we don't have a constant rate of change, if we're able to trace out all these points then, what will the result be? So when we do have constant rate of change and we trace out all the points make a line. So if it's non-constant rate of change, what are you going to get? It's going to curve, right? It's going to curve. And that's the sign, that's the evidence of non-constant rate. Equal changes in v do not give consistent. Equal changes in x do not give a consistent change in v. Okay? So here's a nice contrast, right? We got a nice example of constant rate of change and a nice example of non-constant rate of change to kind of tie up that part of the unit. Okay, any questions on this?
Yeah.
Please.
So for the volume, I
Yeah.
know that you're supposed to plug in what the initial value of x and then the end
Yeah.
the start value of x and end value of x.
And take the change in v.
Alright, so I've not written math out yet, but in my head I keep thinking it's going to end up being, whatever the value of 0.5 is minus 0, because the initial value is 0.
No, in this change, the initial value of x is not 0. The initial value of x is what? 0.5.
0.5? Alright.
So x changes from 0.5 to 1. So you're never going to plug 0 in to get a value.
The first one.
The second one.
But I'm talking about the first one.
The first one. So this is just one particular case where yes, you're going to. your change in volume ends up being the same as the value of the volume at 0.05.
Thanks.
Just that one case. Other questions? Okay, cool. So what's next? So this is a nice transition to talk about functions. So let's talk, and that's what you read about a little bit. So the open top box problem is, we use it as a context for input-output relationships. Input-output relationships. Okay, for example, this is what we just worked on. The input is the length of the square cutout, and the output is the volume of the resulting box. That was the graph on the right, right? That was our relationship on the right side of the screen. Okay, so some input-output relationships are special, and we call those functions. Okay, some input-output relationships are functions, but not all. Okay, so we want to look at these special types of input-output relationships called functions. Okay, if you want to get that down, I'm gonna have you look at the video. Okay. All right. So what makes an input-output relationship function? What's special about a function? Okay. So consider making a call with your phone. What's the input when you make a call with your phone? The number you call, right? The phone number. So here's possible inputs, right? Here's possible inputs. What's the output? Yeah, a person or a place you're going to reach, right? So the input is a number, and the output's a person or a place, right? Mom, friend, pizza, Visa customer service, beg for waves of fees, right? Brother, your ex. These are all possible outputs of numbers. Okay? So how does your phone and service function properly? Every time you dial this number, what happens? You always get this recipient. Every time you dial this number, you always get this recipient. This is a working phone, right? So this is a working phone. You know this. So when you call this number, you want to get your brother every time. When you call this number, you want to get pizza every time. That's a working phone. So here's the idea of a function. For each input, the function has one unique output. For every number that you have, you should get one person or place. You should get one person or place. And that's the idea of a function. For each input, the function has one unique output. Okay? So, but what if you dial this number, sometimes you get mom, and sometimes you get your pizza delivery. Likewise, you dial this number, sometimes you get your brother, sometimes you get your ex. What are you going to do with this phone? You're going to get a new phone or a new service, right? This is not a functioning phone. This is not a functioning phone. Because, why? Because for every input, you get more than one output. Your phone is not functioning, right? It's not a valid functioning phone. So it's violating the definition of a function. But what about this case? Okay, suppose your friend has 2 telephone numbers. Everyone's got a friend like this, right? Well, maybe not so much anymore, but in the transition from landlines to cell phones, many of us had 2 numbers. Many people had 2 numbers. Okay, and so you had like a landline, or maybe a work phone and a cell phone. Likewise, there's different ways to reach Visa customer service. There's many numbers that will get you to that same call center. What about this? Is there a problem? Is the phone functioning correctly? Does it fit the rule for a function? For every input, is there exactly one output? Yeah. So for that number right there, you're always going to get who? That's the requirement. And for that number, it doesn't say that 2 inputs can't have the same output. What it says is, that for every input, you can only get one output. And is that intact here? Is that okay? Yeah. Every input results in one output. The phone functions fine. It's a functioning phone. It's fine. Okay, another example. So you go in the summer, and you're camping several times, and you take some data on temperature and frogs and crickets and the sounds they make. Okay? So here's your data on frogs. Your input is, at different times you hear a number of rivets per minute. So you start the clock and you listen for rivets. And throughout the summer, there were different situations where you heard 2, 3, 4, and 5 rivets. So when you heard 2 rivets, the temperature was 78. That's this point right here. See that? And then, but when you heard 3 rivets, 66 and 91. Likewise, 4 and 5 gave 3 different temperatures at different times of the summer corresponding to that number of rivets in a minute. How about this? A function? No, right? Why? Because the same input is giving multiple outputs. What about this one? Crickets. So here's just 4 examples of 4 points. At the time that you heard 92 chirps, it was 58 out. When you heard 94 chirps, it was 70 out. When you heard 97, it was 82. When you heard 100, it was 97. How about this? Function? You bet. So this is kind of, I'm trying to motivate. So you may have heard this rule before as you study functions, and for every input there's exactly 1 output. So why? What's the big deal about that? This is showing what the big deal about that is. What's the big deal about these special relationships of 1 input and 1 output? So who can say, what's the big deal? Yeah. It doesn't have to be linear. So what is it about that we want 1 output for every input and not more than 1 output? Why? What's that?
Is this accurate and consistent?
Accurate and consistent, and why do we want that?
Reliable.
So, yeah, it's reliable. It's useful, right? What about frogs? Are you going to listen to frogs to figure out what the temperature is? No, right? It's just not. It doesn't function. It doesn't have a function. It doesn't have a function. You're not going to get temperature by listening to rivets. But does the crickets, do they serve a function? They serve a function because if you listen to the number of chirps, you can predict what the temperature is. You see? 1 unique output for each input means that a function performs a reliable function. You see? Okay, cool. All right, so let's go back to our applets on this one. So what about volume and... So is volume a function of length of the square cutout? Is volume a function of, we said it was 11 minus 2x, 8.5 minus 2x times x. So input, what's our input? X, side length, right? X, side length of the cutout. Output, volume of the box. So for this input-output relationship, input is the side length of the cutout. Output is the box volume. Is it a valid function?
Yeah.
Why?
Because there's only 1 output for every input.
If you cut out a square, if you choose a side length, do you get 1 volume resulting, or many volume, or possibly more than 1 volume? There's only going to be 1 volume, right? If you cut out the square side length, fold up the flaps, and make this box, there'll be only 1 resulting volume. Only 1 resulting volume. So yes, a function. So there's another thing called all possible inputs of a function. So in this case, talking about x, all possible inputs in a given scenario. You remember what that's called? What's it called? Maybe you don't. The domain is just, it's just, what are all the possible inputs? In this case, what are all the possible cutout lengths that we could do? So normally to figure that out, we think about what's the lowest possible side length of the cutout and what's the highest possible, okay? So, and we really want to think about this mathematically. What is possible? Not just what makes a valid box, but what is mathematically possible? So what's the lowest possible value of x that is mathematically okay in the situation?
Does it still have a bigger box? Or
No, just mathematically okay in the physical realm. 0 is possible, right? Right? Everyone, hold up a sheet of paper. Ready? You just did it. You just cut out square corners of 0. You see? You just did it. Okay? It's okay. It's just because it doesn't make a box, mathematically, x equals 0 is okay. Don't let it frighten you. So our domain, so we can say x, so 0, so we want all x values, so we know 0 is the least, up to what? So what's the physically largest possible value of x that we could cut?
4.25.
Okay, we're at 11 and 4.25. So let's take a look. Here, let's just do it. Ready? No, but it's 8.5 by 11. Okay, so where does it not possible to make bigger cutouts anymore? Right there. So what value of x is that? Half of the width, okay? In this case, half of the width. What about that situation? What happens in that situation? We cut out the 2 squares, and we're left with a flap, and we fold up the flap, and what's our volume? 0 again, right? It's just like this vertical flap, right? Because there's no sides this way. Okay? So, again, it doesn't make a valid box, but it's physically possible to cut out squares of side length 4.25. Therefore, it's in the domain, mathematical domain. Okay? What about 4.3? Can we cut squares of 4.3? Impossible, because now you can get a 4.3 square here, but then you can't get that over here. Right? You'd be like, you can't do it. What about a square side length of -1/2? Can't do it. You can't have negative, right, distances. So this is our domain of this function, all possible x values. We can have 0, and we can have 4.25, and we can have anything in between. Okay? But we cannot have anything less than 0 or greater than 4.25. So another way to write this is this way. So this is interval notation. Brackets mean include the ends. Parentheses mean don't include. Or you can use inequality notation. Both of these give the domain of this function, all possible values of the input. Okay, what about notation for functions? So that's domain. What about notation? So you can think of this process, this function process, kind of like a machine. Okay, so how is it thought of as a machine? So it's like a machine that takes the length of the cutout and performs something. It does something, right? It has a function. It spits out what? What happens? It spits out the volume, right? So it's this machine that takes the cutout side length and gives you volume. So it takes input and gives output according to a rule. So this is the idea of a function. It takes input, gives a corresponding output. How many outputs does it give for an input? Only one per input. Only one output per input. And it gives that output according to some rule. Okay, so here is our what we call the function definition. So this is our symbolic representation of functions. Really important, okay? This is how we represent functions. Our output is the volume. This F here doesn't have to be F. F's the most common choice. It can be G, H, D, anything. That's the name of the function. That's just the name of it, okay? The input, we see it both here, in this notation over here, X, and in the rule, right? So the rule is an expression in terms of the input, right? It's a rule is an expression in terms of the input. That whole thing is the rule. Sorry if you can't see this. This is saying that X is the input. Sorry, go back. Okay, so this is a function definition. It includes the name, the input, and the rule. So what we often use in what we call function notation is this. right here. The beauty of this is we can represent values with this notation right here without having to crank out numbers and do lots of calculations. We can just represent values in this using this notation. So this that I put a box around, what does it represent? So what value or quantity does it represent, what I put a box around? He said the volume. Agree? You agree? Yeah. Yeah. So this is, when you see f of x, that represents the output of the function. Which output is it? Which output is it? When the what? Input is x. Okay? So if I write f of 2, how do we, so if you saw f, so we're talking about the open top box problem. This function f, when you see f of 2, what does that mean? F of 2. Somebody knew. What is it, Nick? No, in front of me. What's your name? Kevin, sorry. Kevin, so what would f of 2 mean?
I mean that for what's your input of 2, that f of 2 would be your output.
He said that's the output when the input is 2. What do you think? So now tell me that in terms of the situation. So yes, that's right. It's the output when the input is 2. But now retell that to me in terms of the situation.
X equals 2, so you're cutting out like 2 inch squares.
Okay.
So you like just put 2 into the rule.
Yeah, but what does this mean?
That mean
What does that mean? Yeah.
It's the
Jonathan.
volume of the box with the sideline cutouts 2 inches.
Right. See, this is, so everything you said was correct, but what that notation means is the volume of the box. It's the output. It's the volume of the box when the square cutout is 2 inches. Okay? All right, so I want you to get a partner and practice verbally what all these expressions mean. So practice verbally. What do all those expressions mean? Say it out and be specific. Okay, go. And I'm going to start attendance. So I know some names here. Garrison, f of b. Explain to me what f, when you see f of b, what does that mean? Not sure. Jose?
It's the output of the box when the input is b.
Okay, so it's the output of the function when the input is b. What about in terms of the scenario? So is it Eric?
Yes.
Eric. So in terms of the box, what does that mean? F of b.
Would that be the volume of the box?
Which volume is it?
Not sure.
Which volume is it? Is it Sod? Which volume is it?
The b is the input of the s of the chain of the inches,
Okay.
and that's the output.
Right. So this whole thing is, but the whole thing is what?
The volume of the box when the cutout size is b.
That was well said. Did you hear that? This is the whole thing together is the volume of the box. Which volume is it? When the cutout length is b. Patricia, how about f of 3 plus h?
I wasn't sure, but I.
Just do the same thing.
But you're adding h, right? There's a big. You said
So
it's
the whole thing, what is the whole thing?
the volume of the box.
Volume of a box
Cut out of x3 plus 8.
with cutout side length of 3 plus h. Is it okay? That's it. It's the volume of the box when the cutout side length is 3 plus h. Now this one's different. What is this now? Jonathan wants to go for this one.
It's the volume of the box plus h when the side length cutout is 3 inches.
It's the volume of the box plus h. So h is like a volume or like a inches?
Probably be another volume.
Yeah, so it's like adding more volume to the box that has a cutout side length of 3. So the whole thing is what he said. It's the volume of the box with 3 with side length cutout of 3 plus some more volume, plus some more volume. Yeah, Jeremiah.
So if h has the same value on the last two, does that mean that
Okay, so he's asking, I think what you're asking is, if you add h to the square cutout, would that be the same as adding h to the volume at the end?
No.
Would that be the same? No, it wouldn't. It would not. Yeah, so adding h and then finding the volume will give a different total volume than finding the volume when x is 3 and adding h more volume. Those will be two different values. Yep. Question?
Done with the f of 3 plus h, with the h outside of the parentheses, you're adding h to the end of the rule, as opposed to including it in the rule, right?
Okay, so yeah, so instead of this being now 3 plus h each time, it would be like taking that with 3 in it and plus h. Yeah, exactly. Yeah, good. Is there another question? Okay, so let's talk about the language. A little bit of time left. So the language of input and output. Okay, so we say P is a function of S. Okay, so this is like F is a function of X. I'm sorry, V. So for our previous example, we would say V is a function of X. Which is the input and which is the output?
S is the input and P is the output.
X, it makes sense, right? Because it's like when you say in just everyday language, when you say is a function of, you're saying is dependent on or comes from, right? So the volume is dependent on or comes from whatever we choose the side length. So this should make sense that output is a function of input. Output depends on or results from input, right? So if we say P is a function of S, then what is the output? P is the output and S is the input. If we say P in terms of S, P in terms of S, P, so what is the input and what's the output?
Still the output.
Yeah, it's still, because in terms of S means like a formula with S's in it. Right? In terms of S. So that indicates that S is the input, right? So P in terms of S means that S is the input and P is the output. P with respect to S. That's another way we can talk about functions. P with respect to S. Again, the output here is P with respect to the input of S. So, you might conclude that any way you phrase it, the output will always come first. In these three phrases, yes, the output is always P and the input is always S. But what if I said that the function converts P to S? Then what's the input? If the function converts the quantity P to the quantity S, then what's the input? Now P is the input and S is the output. So there are lots of ways to phrase it. Okay, lots of ways to phrase it. You have to think about it every time. But here's three common ways that we'll phrase it. And for these, the output is first, and the input comes later. This is the most common. P is a function of S. Means output is a function of input. Okay, so while I finish up attendance, go to page 83 in your book. Just a little practice on this. So page 83, I'll finish up attendance and then we'll call it a day. What? Oh yeah, sorry. We'll cut it. Yeah, start number 2. These are just some examples of what we just talked about. You're determining what's the input and what's the output. So start on number 2, bottom page 83. Just talk through those. You don't have to write, and then turn to the next page and just talk through them. You're practicing identifying the input and the output. And then also saying, is it a function or not? Is it a valid function or not? Okay, go. Okay, Mariama. Dominic. Mechi. Robert. Marcel. Jose, Macy, Ethan, James is here, Cooper's here, Patricia, Chris, Christy, Chuck, Sang, Nick, where's Nick? Kunlu, Kevin. Okay.
That's the final, that's like
Okay, so I think, sorry, I forgot to collect the homework at the beginning. So, you know you're gonna fold it. Robert's done a good job here. You're gonna fold it right down the middle. Turn the open side to the right. Give your Chris a favor, a clean left edge. Take all the fringe sheets again, clean left edge. Fold right down the middle. Turn open side to the right. And then what are we doing? Name, 9 a.m. and dates.
The front of the page should be inside.
That's it. So take your papers like this in order. Fold them right towards you like this and turn to the right. Yeah. Yeah, I got you. I know you. Okay. Everyone, so name, time, and date. And then he's got a few more quizzes to hand back. If you want to stick around a minute, and I can answer any of these questions.
Hey man.
That just kind of gave you some practice on the workbook. If you want to stick around and talk about those, you're welcome.
That's the homework. Michael?
Thursday's homework is not posted yet, but it will be in the next hour. Okay? Thursday's homework will be up in the next hour.
Alright, so like what I was thinking
Jennifer?
too.
The same.
I feel like one of these isn't because like it's like